Okay, problem two. The Ralph-O-Matic, which is this new amusement park ride I've got that basically spins people in a circle. I had some questions about why it's called the Ralph-O-Matic. And Ralph, to me, or to most people my age anyway, Ralph is slang for vomit. So, things say things like, oh man, I'm going to Ralph. Oh man, that cheeseburger must have been, something bad. I'm totally going to Ralph now. Okay? That's where it comes from. I don't know why it came to be called Ralph. Maybe there was somebody named Ralph who always had problems with this, and so it came to be called Ralph because of him. I honestly don't know. But anyway, there you go. So what happens is this thing spins these gondolas around in a circle. These are cables here, and they're kept stretched taut by the spinning of the gondola. So what we need to do is calculate the minimum speed at which this thing could be spinning and still keep the cables taut all the way around, because they have to have a tension of at least 0. So 0 is sort of the minimum tension they can have before, if they try to get negative tension, they'll just go slack and go, So the radius here is 10 meters, and so this is actually a deceptively simple problem. The first thing to think about is at what point are you most likely to have this problem with the cables going slack? And if you think about it for a bit, you'll realize it's at the very top. That's when you're most likely to have, if you've probably done this before, where you spin something in a vertical circle. So you can imagine like standing there spinning a piece of rope or something, and if you try to spin it as slow as possible without it going slack, and you'll notice that the top is the place where it first starts going slack. So we're going to look at a gondola at the very top. So here is our, let's see, so here's our little, there's our hub, and we have a gondola at the very top, and it's going in a circle roughly like this. Okay, and radius like that, and its speed, it's going this way with speed v. It's going in a circle at a constant speed v, the radius r. What is the acceleration? Okay, I know, don't tell us, Dr. Smith, we'll get it. Okay, a equals v squared over r. Okay, so that's all cool. Now, let's look at the forces acting on the gondola when it's up there at the top. First of all, you got gravity, that's always acting. And then you got tension from the cables. So let's draw a free body diagram for a gondola. And there are no other forces acting on this thing. It's just gravity, just weight and tension. That's all. You might think of centrifugal force or something like that, like you're gonna have a force going outward. But that's your intuition playing games with you and being wrong. There is no force going outward. What you feel is the normal force of the gondola pushing up on your butt if you're sitting in this thing, but you don't actually, there's no centrifugal force. That's just the gondola trying to push you in the circle as it's pulled by tension and gravity that way. So FBD for the gondola, and I'm going to do the usual x, y here, and so accordingly x, y. Here is our gondola, and we've got mg pulling down, and we've got the cable tension pulling down. Okay, so sum of forces in the y direction is going to equal the mass of the gondola. The gondola has mass m. Okay, and it's going to be going down, so the y acceleration is actually going to be negative. So this is a negative, this a is negative, so equals negative ma. So let's see what we got. Negative mg, oh sorry, that's right there, and negative t minus t equals negative ma, which means a equals g plus t over m. Now we are at a point, we said, where we are, you can imagine we're going as slow as we possibly can, but the condition is we want to keep the tension in the cables at least 0. So you can imagine when we're at the very slowest, this point up here, at the very top, we're going to get the tension to go down to 0, or very close to 0. So we're going to say here tension equals zero. There we go. Tension equals 0. Cross that out, and then we're going to get just A equals G at this point. Well, now, isn't that convenient? A also equals V squared over R, right? So this is the A we found from our force balance. The A generated by these forces here when the tension's 0. A is just G. And the acceleration needed to keep it going in a circle is V squared over R. So now we can do V squared over R, which equals A, which equals G. And we can just, cut out the middleman, so to speak. So ignore that. And what we get is V squared over R equals G. That's an R, trust me. Okay, and V squared equals GR, which then means V equals square root of G times R. And I said you could use G equals 10 meters per second squared. Sorry, that's a 3 there, meters per second squared. And I said R is 10 meters. So V is square root of 10 meters per second squared times 10 meters. And you can see then that meters, seconds, it all checks out. So V, that's too low. Let's see. Well, I'll just do it right here. V equals 10 meters per second is our answer. So that is the absolute slowest the gondola or the thing can be spinning in order for the gondolas to stay fully splayed out. And any less than that, gondolas will, the cables will go slack, gondolas will be in free fall, people will be falling out, mass panic will ensue, bloodbath, mayhem, and all that.